Imagine, the James Webb Space Telescope, launched December 25, 2021, points at a distant galaxy 300 million light-years away and watches, infrared camera rolling, as a black hole tears a star apart. Not the aftermath. Not the echo weeks later. The moment of destruction. Here's the paradox: despite light taking 300 million years to reach us, meaning we're watching something that happened before dinosaurs walked Earth, and despite the event unfolding over months in the star's reference frame, relativistic physics would compress what we see into a violent, rapid crescendo. This hasn't happened. But the physics says it could. How is it possible to witness stellar death across hundreds of millions of light-years? And what would we actually see if we pointed our most powerful infrared telescope at a tidal disruption event in progress? The James Webb Space Telescope launched Christmas Day, 2021. But here's the counterintuitive detail: JWST wasn't designed to stare at black holes eating stars. Its primary mission: observe the universe's first galaxies, 13+ billion light-years away, their light stretched into infrared by cosmic expansion. Tidal disruption events, TDEs, weren't a priority. They were considered too rare, too unpredictable, and too short-lived for a telescope that must schedule observations months in advance. But a special circumstance changed the game: JWST's infrared vision pierces dust. When a black hole shreds a star, the debris forms an accretion disk, superheated gas spiraling inward at relativistic speeds. That disk glows in X-rays and UV, but it's also surrounded by a cocoon of dust and gas heated to thousands of degrees, radiating in infrared. Ground-based telescopes and Hubble see the visible light. X-ray satellites like Chandra see the high-energy emission. But JWST sees the warm dust, the infrared signature of stellar destruction that other telescopes miss. 5 achievements that prove JWST could detect TDEs. Achievement 1: Deep Galaxy Surveys. JWST's deep field images routinely capture thousands of galaxies per frame. Statistically, several of those galaxies likely host supermassive black holes. If a TDE occurs in one during observation, JWST would catch it serendipitously. Achievement 2: Time Domain Infrared Monitoring. Unlike Hubble, JWST can revisit the same field weeks or months later with identical instrument settings, enabling before and after comparisons. A sudden infrared brightening in a galaxy core would flag a TDE. Achievement 3: Spectroscopic Fingerprints. JWST's NIRSpec can take spectra of distant point sources. If a TDE is detected, follow-up spectroscopy would reveal the composition of the shredded star, hydrogen, helium, carbon, oxygen, and measure Doppler shifts showing gas spiraling at 10 to 30% light speed. Achievement 4: Mid-infrared Dust Detection. JWST's MIRI instrument detects 5 to 28 micron infrared, exactly where warm dust around a TDE accretion disk radiates. MIRI could map the dust distribution, revealing the geometry of the debris cloud. Achievement 5: Multi-wavelength Coordination. JWST doesn't work alone. When X-ray satellites detect a TDE flare, they alert the astronomy community. JWST can then request directors discretionary time, emergency observations that bypass normal scheduling, to catch the infrared evolution. 2 observatories. 2 wavelengths. 2 completely different views of the same cosmic violence. Chandra's view, Chandra X-ray Observatory, launched 1999, detects the hottest material, gas heated to millions of degrees as it slams into the accretion disk at near light speed. Chandra sees the TDE's peak energy, the X-ray flare that spikes within days of the star's destruction, then fades over weeks. Chandra caught at 2019 DSG in the Galaxy 2 masks J2057029 +1412165, a TDE 690 million light-years away. The X-ray brightening was dramatic. The black hole went from invisible to blazing in X-rays, then dimmed over 200 days. But Chandra sees only ionized gas, plasma so hot electrons are stripped from atoms. JWST's hypothetical view, JWST would see the warm material, dust and gas heated to thousands of degrees, not millions. This emission peaks months after the X-ray flare, as ejected debris expands, cools, and forms a dusty shroud around the accretion disk. JWST would watch the TDE's echo, the infrared glow rising slowly as the initial explosion's energy heat surrounding material. Current status comparison: Chandra, 25 years operational, aging but functional, detected roughly 100 TDE candidates. JWST, 3+ years operational, has not yet been formally tasked to observe a TDE in infrared, but the capability exists. Here's the relativity trick: a TDE unfolds over months in our reference frame. That may not seem like much, just watching a light curve rise and fall. But imagine you're the star. You're orbiting a supermassive black hole, same as you've done for billions of years. Then, in a span of hours, the time it takes you to make one final orbit, tidal forces stretch you into a stream of plasma 100,000 kilometers long. From your atom's perspective, you go from star to noodle to accretion disk in less than a day. From our perspective 300 million light-years away, we watch the afterglow flicker for months. What Chandra achieves, catches the initial violence, the X-ray scream of a star dying. What JWST could achieve, watches the aftermath, the warm infrared glow of stellar ash spreading through space. Two commonly confused terms: event horizon versus tidal disruption radius. Think of the event horizon as the point of no return, the boundary where escape velocity exceeds light speed. Anything crossing it is gone forever, invisible to the outside universe. For a supermassive black hole of 10 million solar masses, the event horizon has a radius of about 30 million kilometers, roughly 0.2 astronomical units, 1/5 the distance from Earth to the Sun. But tidal disruption doesn't happen at the event horizon. Think of the tidal disruption radius as the spaghettification zone. It's the distance where the black hole's gravity varies so steeply from one side of the star to the other that tidal forces, differential gravity, rip the star apart. This radius depends on the star's size and the black hole's mass. For a Sun-like star orbiting a 10 million solar mass black hole, the tidal radius is roughly 100 million kilometers, about 67 cents, more than 3 times farther out than the event horizon. The star dies before it reaches the point of no return. The exact moment of transition, a star on an elliptical orbit swings toward the black hole. Far away, it's safe, tidal forces are negligible. As it passes the tidal radius, forces on the near side exceed forces on the far side by more than the star's self-gravity can withstand. The star stretches. Leading edge accelerates inward. Trailing edge slows. Within hours, the star becomes a stream, half the material falls inward, half is flung outward on hyperbolic escape trajectories. Significance: only about half the star's mass is actually consumed. The other half escapes at high velocity, carrying away energy and enriching the surrounding galaxy with heavy elements forged in the star's core. This is why TDEs are messy, not clean consumption, but violent, asymmetric destruction. Multi-stage timeline: T equals 0 hours, star crosses tidal radius, begins stretching. T equals 2 to 6 hours, star fully disrupted into stream, debris orbits black hole in eccentric ellipse. T equals 1 to 10 days, leading edge of debris stream completes orbit, collides with trailing edge, shocks heat gas to millions of degrees, X-ray flare begins. T equals 10 to 100 days, X-ray emission peaks as accretion disk forms, UV and optical light brighten. T equals 100 to 365 days, X-rays fade, infrared emission from warm dust rises as debris cloud expands and cools. This is JWST's window. T equals 1 to 10 years, infrared fades, accretion disk depletes, the black hole returns to quiescence, until the next star wanders too close. Restate the core mystery. How could JWST detect an event 300 million light-years away that unfolds over months in a region smaller than our solar system? The answer: extreme light-collecting power plus patience. The transmitter analogy. Think of the TDE accretion disk as a cosmic lighthouse, small, a few million kilometers across, but absurdly luminous. At peak, a TDE can outshine its entire host galaxy, radiating 10 ergs per second, equivalent to 1 billion suns. Most of that energy is in X-rays and UV, but 10 to 20% gets reprocessed by surrounding dust into infrared. That's still 100 million solar luminosities in JWST's wavelength range. Even across 300 million light-years, that's detectable. Signal travel time perspective ladder. Layer 1. Light leaves the TDE accretion disk, travels across the host galaxy, 100,000 light-years, scattering off dust and gas. Some infrared photons escape the galaxy. Travel time for the photons to clear the galaxy, roughly 100,000 years, though they left recently in the galaxy's rest frame. Layer 2. Those infrared photons cross 300 million light-years of intergalactic space, stretching slightly due to cosmic expansion. Travel time, 300 million years. The photons arriving at JWST in 2025 left during the Carboniferous period on Earth, when giant insects ruled swamps and the first reptiles emerged. Layer 3, photons reach JWST's mirror at L2, 1 million miles from Earth. JWST detects them, converts the signal to digital data, and transmits to Earth via the Deep Space Network. Travel time for data downlink, 5 seconds. We're seeing an event that happened 300 million years ago, compressed by observational geometry into a months-long infrared brightening. Signal degradation by inverse square law. A TDE at 300 million light-years is at a distance of roughly 2.8 times 10 superscript 2 meters. Even a billion solar luminosity infrared source diminishes to about 10 superscript 1 watts per square meter at Earth. JWST's 25 square meter mirror collects roughly 2.5 times 10 superscript 1 superscript 3 watts total, a quarter of a trillionth of a watt. But JWST's detectors, chilled to 7 Kelvin, can count individual photons. Over a 10,000 second, 2.8 hour, exposure, that's enough signal to detect the TDE and measure its spectrum. How massive the receiver must be. JWST's 6.5 meter segmented mirror is close to the practical limit for space telescopes with current launch technology. Future concepts, like the proposed DEVOUR with a 15-meter mirror, or HabX, would detect TDEs at even greater distances or in finer detail. Ground-based infrared telescopes are blocked by Earth's atmospheric water vapor, which absorbs the exact wavelengths JWST targets. Only a space-based infrared observatory can play this game. The Global Coordination Network. When an X-ray satellite like SWIFT detects a TDE candidate, it issues an automated alert to the astronomer's telegram, a global notification system monitored by telescopes worldwide. Within hours, observatories coordinate, X-ray satellites like Chandra and XMM Newton for high-energy emission, UV/optical observations from Hubble and ground telescopes for visible light curves, infrared from JWST if director's discretionary time is granted for warm dust, radio telescopes like VLA and ALMA for late-stage jet emission. This multi-wavelength coordination allows astronomers to reconstruct the full TDE timeline, from initial X-ray flare to infrared echo to radio afterglow months or years later. JWST's role would be capturing the 100 to 365-day infrared peak, the phase other telescopes miss. Here's why the normal solution doesn't work for capturing TDEs. JWST can't respond instantly. Hubble, in low Earth orbit, can be retasked within days for urgent targets. JWST, at L2, operates on a rigid schedule planned months in advance. Observation sequences are uploaded weeks ahead, coordinated with the Deep Space Network downlink windows and thermal constraints. A TDE alert might come today. JWST's next available observation slot might be 3 months away, potentially missing the infrared peak. But JWST has limited director's discretionary time, emergency slots reserved for unpredictable, high-priority events. TDEs qualify. The constraint isn't just scheduling, it's fuel. Alternative power source, JWST's MMRTG, the same plutonium RTG as Perseverance, provides 110 watts and will last decades. But the limiting consumable is hydrazine propellant for station keeping. Starting capacity in 2021, 240 liters, budgeted for 10 years. Current capacity in 2025, roughly 210 liters, 87.5% remaining. The Ariane 5's precision saved fuel. JWST now projects 20+ year lifespan. Conservation measures, reaction wheels handle most pointing, saving thruster fuel. Optimized slew paths between targets minimize fuel burn. Momentum dump scheduled efficiently to reduce thruster use. Emotional artifact with finality, there will come a day, perhaps in the 2040s, when JWST images its final TDE. The infrared glow will be recorded, the spectrum analyzed, the data transmitted home. Then, fuel exhausted, JWST will drift from L2 into an independent solar orbit, carrying the names of 10,000 engineers on a microchip, forever watching the universe, but unable to tell us what it sees. Minimal current operations. As of 2025, JWST operates at full capacity, all instruments functional, full science schedule. Projected declining trajectory, 2025 to 2035, full operations. Could observe 5 to 10 TDEs if alerts arrive and director's time is granted. 2035 to 2043, fuel-limited operations. Fewer target changes, prioritization of high-value observations. 2043 plus, fuel depletion. Silence. Every potential TDE observation exists within this shrinking window. Problem 1, Micrometeoroid strikes, ongoing. Since May 2022, JWST's mirror has been hit 6 times by micrometeoroids, tiny, fast-moving debris. Why critical? Each impact creates permanent optical aberrations. Mirror segment C3's 5-micron crater slightly defocuses starlight, reducing sensitivity to faint targets like distant TDEs. Automated solution, wavefront sensors detect aberrations within hours. Onboard software commands segment actuators to adjust by nanometers, compensating for damage. Resolution, image quality remains at 99% despite impacts. Ongoing threat, strikes occur every roughly 2 months, 4 times faster than predicted. Cumulative damage will eventually degrade JWST's ability to detect faint infrared sources. TDE implication, each strike makes it harder to see distant TDEs. By the 2030s, only nearby, bright TDEs may be detectable. Problem 2, MIRI Grating Wheel Friction, 2022. MIRI's grating wheel, critical for 5 to 28 micron spectroscopy, showed increased friction at certain positions. Why critical? MIRI is the only instrument that can detect warm dust emission from TDE debris clouds. If it fails, JWST loses its unique TDE capability. Diagnosis: engineers spent 3 months testing across the 5-second Earth, L2 signal delay. Found that -266°C operating temperature caused lubricant issues in specific wheel positions, 15 to 25 degrees rotation. Manual fix: operational procedures now avoid high friction zones. MIRI uses longer exposures with stationary wheel positions. Resolution: MIRI continues functioning in all modes with adapted procedures. Friction hasn't worsened. TDE implication: MIRI's warm dust spectroscopy is essential for confirming TDE infrared signatures. Its continued health determines whether JWST can uniquely contribute to TDE science. Future Problem 3, Detector Degradation, Anticipated 2030s. JWST's HGC-DT infrared detectors accumulate radiation damage from cosmic rays, gradually increasing hot pixels and reducing sensitivity. Proactive monitoring: software flags damaged pixels, using adjacent pixels instead. Anticipated solution: none, hardware can't be repaired. Software can compensate up to roughly 15 to 20 years of damage. Expected extension: if degradation is slower than models predict, JWST could observe TDEs into the early 2040s. TDE implication: faint, distant TDEs will become undetectable as detector sensitivity declines. Priority will shift to nearby, bright events. Ongoing challenges compound: micrometeoroid damage accumulating, MIRI grating wheel wear, detector radiation damage, propellant depleting. JWST projects fuel exhaustion, 2043 to 22 years post-launch. Time remaining from 2025, 18 years. But TDEs are rare, roughly 1 per 10,000 galaxies per year. JWST's field of view might catch a few dozen TDE candidates over its lifetime. Confirmed TDE detections requiring director's discretionary time and multi-wavelength coordination. Perhaps 5 to 10 total before fuel runs out. Every TDE that flares in JWST's observable universe during these 18 years is a fleeting opportunity. Miss the infrared peak, 300 to 365 days after the X-ray flare, and the science is lost. The clock ticks not just for JWST, but for a cosmic phenomenon we've barely begun to understand. When fuel depletes in 2043, JWST drifts into solar orbit, silent, watching TDEs occur across the universe with no way to tell us. The stars will keep dying. The black holes will keep feeding. But our infrared window will close. JWST launched December 25, 2021, designed for 10 years. It may last 22. Compare its specs to modern tech: storage, 68 GB, less than a smartphone. Processing, 25 MHz, slower than a 1990s PC. Bandwidth, 28 megabits per second, slower than home Wi-Fi. Mirror precision, 10 nanometer alignment, 30,000 times better than LASIK. Ancient computation. Unmatched vision. JWST hasn't captured a black hole devouring a star in real time, yet. But the physics says it could. The instruments exist. The sensitivity is there. The infrared window is open. We're waiting for the universe to cooperate, for a star to wander too close to a black hole in a galaxy JWST happens to be watching. When it happens, we'll see what no generation before us has seen, the infrared afterglow of stellar death. The warm dust spreading from a shredded sundae. The echo of gravity's ultimate violence. Until fuel runs dry in the 2040s, JWST will keep watching. Waiting for the universe to glitch. Waiting for a star to fall. We haven't seen it yet. But we're looking.